Hello, in this video I'd like to ask and answer kind of an interesting question, which is, what is a complete set of rules for manipulating formulas that we need in order to work with polynomial expressions? So a polynomial expression can be constructed recursively, starting with some collection of numbers. It could be integers, could be real numbers. We're pretty flexible on this account. And we'll add in just one variable, but again, we're flexible on that. You can adapt this argument to add in as many variables as you want. And then, of course, addition, subtraction, and multiplication. Technically, if you're working with polynomials, you're going to want to have positive integer exponents, but I'll avoid having them just to keep everything as simple as possible. So we can, starting with these atomic expressions and combining them with these operations, produce a whole bunch of different expressions that ultimately wind up representing polynomials. Where again, I've cheaply avoided having to deal with exponents by just writing x squared as x times x. So the question that I'm interested in is, if we have another polynomial expression that's also been recursively built up in this way, how do I tell if these two polynomial expressions are equal to each other? In the sense of real polynomials, in that if we plug in any value for x, into one expression and we plug it into the other expression, we're going to get the same values as a result. We know how to deal with this sort of situation. We take our polynomial expressions and we convert them into polynomials. And we do this working our way from the inside out. First, we turn this sub-expression here into a corresponding polynomial, and we also have to distribute this minus sign to turn that into a polynomial, and we can combine everything. We combine like terms, and then we get our answer. And then if we had another polynomial expression, we could do the same thing, working from the inside out, turn it into a single polynomial, and then compare if the results are equal to each other as polynomials. This is all well and good from an informal perspective, but what if we're trying to teach a computer how to do algebra? One of the projects that I've been working on for a while now is what I like to call a computation assistant. It allows you to select pieces of a formula that you're interested in applying a rule to, select which rule you want to apply to that piece of the formula, and then it automatically applies that rule correctly for you. This is an intermediate stage between working everything out by hand, where it's possible to make mistakes, and working things out on a computer where you don't get the same amount of control and flexibility about what order you apply operations in, and you don't get the practice of picking out what order to apply operations in. My hope is that this can be a very powerful educational tool when used correctly. And so if I want this system to be at all usable, it at the very least has to be the case that if we have two expressions that represent the same polynomial, that we can convert one to the other simply by applying the rules within the system. And so in order to do this, I need to be incredibly pedantic about what rules I'm actually using at what steps in working out these basic algebra problems. This is going to be similar to, but not quite the same as, working out complete axiomatizations for various logics, so I thought I'd throw it into this video series here so that we can get some practice thinking about these sorts of problems in a situation where we have really good intuition about what's going on. At the core of this program are two fundamental facts about algebra. The first is that if we have some sort of equation like p minus 1 times p plus 1 is equal to p squared minus 1, that's true for any value of p. This isn't just a simple algebraic equality between two expressions. This is actually a template for rewriting algebraic expressions. We can plug whatever we want in for all of these p's, and provided we plug the same thing in for each of the p's, we're going to get a new true equality within algebra. And we can do this with numbers, so like 10 minus 1 times 10 plus 1 is equal to 10 squared minus 1, but we can also do it with algebraic expressions. We can, for instance, plug in 2x for p, and that's perfectly fine. It gives us a new true algebraic fact, that these two expressions are equal to each other. And we can plug in whatever we like as long as it's of the appropriate type for all of these p's here. Notice that there's a little bit of fiddling with parentheses. We don't have parentheses around p here, and we do have parentheses around 2x here. I'm just going to assume that the computer already knows how to deal with parentheses and is already thinking of these sorts of expressions as tree-like data structures. How to convert sequences of characters into these tree-like data structures and back is a completely different question. So now that we know that these two expressions are equal to each other, anywhere within a larger formula that we see one of them, we can replace it with the other and have an equivalent formula. In this case, that's exactly what we did here. We can see this in action in one of my computation assistant demos here. So together, these two replacement rules actually serve as kind of a universal replacement rule that we could apply in order to do any sort of algebra, provided that we have enough basic equalities within our toolkit. Right? This first rule that if we have an equality within our toolkit, we can replace each variable with something, and we have to replace every instance of the same variable with the same thing to get a new true equality. And then if we know that two things are equal to each other, we can replace any instance of one with an instance of the other. Having these two universal rules combined in the appropriate way allows us to just focus on the question of what basic equalities do we need in order to make all of this work. So how should we be thinking about this problem? We will use this notation here to indicate that one polynomial expression is equivalent to another polynomial expression. Our goal here is to take the set of all polynomial expressions and divide them up into a bunch of little groups based on whether or not they're equivalent to each other. So any two polynomials within the same group are going to be equivalent, and any two polynomials in different groups are not going to be equivalent. And we're going to want to pick out a single representative from within each polynomial equivalence class. That representative is going to be called a canonical form, and it's going to be exactly what you expect it to be. It's going to be just the polynomial that all of the expressions within this class represent. So all three of these polynomial expressions are within the same equivalence class, and our intuition says we're going to want something like this to be the canonical form for all of these different polynomial expressions. It's actually going to be a little bit easier if all of our monomials have coefficients, and everything's a sum, so instead of subtracting one, we're just adding -1. So our goal is going to be that this expression here is the canonical form for all of these different polynomial expressions, which all represent the same thing. Our process is going to look like this. First, we're going to try to formally define what we mean by canonical form, and we need to do this incredibly formally, incredibly carefully. It's very common, because we've worked with polynomials for so long, to be very casual with them, right? Leaving off leading coefficients, rewriting sums as differences, and we know how to deal with these sorts of things. But if you want to prove things, it helps to be really pedantic about what we mean by a canonical form. Remember that our goal is that there should be exactly one canonical form for this entire polynomial expression equivalence class. Step 2 is to keep track of all the rules that we need in order to convert a polynomial expression into canonical form. In line with our intuition, this process is recursive, working from the inside of a polynomial expression outwards. We just have to pay very close attention to all of the rules that we use in all of the steps. That allows us to make sure that there's a sequence of steps that will get us from any of these equivalent forms into the canonical form. We just have to make sure that all of these steps are reversible, so that if we wanted to get from this form to this form, we could follow all of these steps to get to the canonical form, and then follow all of these steps backwards to get to this form. And that will complete the proof. Let's get started by formally defining what we mean to be a polynomial expression in canonical form. Again, following along with our intuition, a polynomial expression is in canonical form, that is polynomial form, if it's a sum of terms of the form some coefficient out front times x multiplied by itself some number of times, where that number of times could be 0, in which case it's just this number out front. Again, we always require this number out front, even if it's 1, even if it's -1, although I guess we should require that that number is non-zero. At this point, we still have a little bit of flexibility in terms of defining our canonical forms, because we could have two terms with the same number of x's, or we could shuffle the terms around. So we'll require that the number of x's that appears in each term in this sum is strictly decreasing. So there are no repeats, and it goes in a well-defined order. So then the question is, what rules do we need in order to get every polynomial expression into canonical form? Well, let's start off with the atomic expressions. If we have just a number, we're already in canonical form. This is already a sum. It's a sum of length 1, but that's okay. It's a sum. It's a sum of terms of this form. There are 0 x's, and we just have the constant out front. So that's perfectly fine. On the other hand, if we have x, this is actually not in canonical form yet. We need to apply a rule that allows us to turn this into 1 times x, which is in canonical form. Our exact choice about what canonical forms we use are going to slightly vary the argument. One notion of canonical form that we could have chosen instead would turn this into 1 times x plus 0, but we're not going to do that. We're going to require that all of these terms be non-zero. Oh. I need to add one more thing. I need to add that it could be 0. Again, all sorts of fiddly details show up that you wouldn't expect when you're working through these sorts of proofs. You would think, oh, I understand polynomials. I have a really good grasp of how they work. And then you actually go to write a computer program to do something as simple as, given a list of coefficients, print out the polynomial in like the form that a mathematician would actually write it in. And oh my goodness, this really simple function is real nuisance to write because of cases like this. But anyway, back to our atomic expressions, we need to add in a new rule that p is equal to 1 times p for any polynomial expression p. We'll toss that into our list of rules. And now we need to look into the recursive construction of our polynomial expressions. Suppose that we have some polynomial plus some other polynomial. Well, we need additive associativity and commutativity in order to get like terms next to each other, and then additive associativity again to put those like terms in parentheses. And then we just need a way of turning terms of the form a times x to the n plus b times x to the n into a plus b times x to the n. You can actually do this with a little bit of multiplicative associativity, to put parentheses around here, and then actually using distributivity in reverse to factor out a common factor of x to the n. And then if you're doing this on a computer, you need a special rule that allows you to turn a plus b, where a and b are numbers, into the actual number that a plus b is. And then finally, don't forget this step, we need to be careful if a plus b is equal to 0, we need to get rid of the term entirely. So we need an extra rule that says 0 times p is equal to 0, and that if you have a 0 in a sum, you can get rid of it, added into our list of rules. If you have a polynomial expression that's a product, to get it into canonical form, you first need to get each of the parts of the product into canonical form, and again do this recursively. And then here I'm going to use x to the n to abbreviate x multiplied by itself n times, but it's just an abbreviation, it's not a notational thing. If we want to multiply these two together, all we need to do is distribute them. We take this polynomial here and we distribute it out to each of the terms in here, and then we have each of these terms times this polynomial, and so we distribute it back. And so this actually saves us from foiling. You technically don't need to cover foiling in an algebra class, although you really should. And then once you do this distributivity and maybe a little bit of associativity, you're going to get a big long sum of a bunch of terms of the form some monomial from the first polynomial times some monomial from the second polynomial. And remember that these are just products, so we just need to do a little bit of multiplicative associativity to turn this into, well, to get rid of these parentheses. And then a little bit of multiplicative commutativity to get the constants out front. When we put these two next to each other, again, it's just a long string of x's multiplied by each other, it automatically becomes x to the power of n plus m. If you had a special notation for exponents within your language, you need to add a special rule in that x to the n times x to the m is x to the n plus m. But again, this is just shorthand notation. This is not actually within the language itself. And then finally, of course, you'll want some sort of way of calculating this product to actually turn this into the coefficient that you want. And then you need to be able to combine like terms within this long sum, which again is just a distributivity applied in reverse. And then again, you need to get rid of the resulting terms that wind up equaling 0. But we already have all of the rules that we need in order to do that. There's a few more steps left. What happens if we have a sum of more than two polynomials? We just need additive associativity to turn this sum here into this sum here, and then we can turn this into canonical form, and then once this is in canonical form and this is in canonical form, then we can turn the whole thing into canonical form using our binary addition process. Similarly, if we have a product of a bunch of polynomials, we can use associativity in order to turn it into this product here, and then turn each of these individual smaller products into canonical form, working from our way inside out. And then finally, don't forget subtraction. If we have an expression of the form p minus q, or just negative q, because we'll also throw in negation as well, we need to be able to turn these into p plus -1 times q, and this one into just -1 times q. In order to convert this into canonical form, we first convert it into this form, then we convert p into canonical form, -1 is already in canonical form, and q into canonical form, and then we turn this into canonical form, and then we turn this into canonical form. Similarly here, we turn this into this, and then we turn this into canonical form, and then we know how to turn products into canonical form. And that should be it. The set of rules that we've been collecting suffices in order to turn any polynomial expression into canonical form. All of these rules are reversible because really they're just, they're templates to be plugged into our more general rule of identifying a subexpression and replacing it with an equivalent subexpression. And so we can find our way from any one polynomial expression to any other polynomial expression via the intermediate step of the canonical form. One can, of course, ask some interesting questions and use this same technique to deal with them, such as what happens if we actually want to add x to the n as a notation, where we still require this exponent to be a positive integer, but we allow it to actually be part of our system. Does it suffice to add in the rule that x to the n times x to the m is equal to x to the n plus m? You might think that it does, but actually you also need to add in a rule for x to the first. And again, the way that you can figure out that that's also important, that you also need to remember to add that rule into your list of rules, is by working step by step through the process of creating a polynomial expression recursively, and then actually working out what the process is for converting it into canonical form. You may also be familiar with a canonical form if we add in division into our collection of operations. You need to be a little bit careful about division by 0, and in particular, it's really gross. Technically speaking, x squared divided by x squared is equal to x divided by x, but this isn't equal to 1, so you need to add in some really tricky rules in order to deal with canceling within these sorts of fractions in order to get a unique canonical form. But it is possible to get a canonical form for these expressions where you take polynomials and you add in division. These are just rational functions. It's just a polynomial divided by another polynomial where you're careful about common factors. There's a hope that we can expand this procedure to include all of algebra and precalculus. This sort of rules-based, identify sub-expressions and apply transformations to them process works really well in calculus. And so one might hope that it can also work really well in the sorts of formulas that we actually give students to work with in calculus problems, so that we could create a complete computation assistant for a calculus class. Unfortunately, I'll call an expression a precalculus expression if it can be built up starting from atomic expressions that are rational numbers, pi, or the variable x, and then build it up using addition, multiplication, subtraction, and negation, and then also the functions sine and absolute value. And it's actually a known result that determining if two precalc expressions are equivalent to each other is undecidable. Through a very long and convoluted process, one can take a Turing machine whose halting problem is undecidable and translate it into an expression that it's undecidable if it's equal to 0 everywhere. The proof of this is very long and required the work of a whole bunch of mathematicians building up on top of each other, including the negative result to Hilbert's 10th problem. It turns out that working with natural numbers is really tricky, and not just the first order logic of natural numbers, but just polynomials on the natural numbers or on the integers. Well, we have polynomials, and then sine somehow allows us to capture integers and natural numbers in that way. And so if there was a canonical form, at least a nice canonical form for this class, then we would be able to determine if two expressions are equivalent to each other just by getting them into canonical form and then seeing if the canonical forms were the same. So there is no nice canonical form for these precalc expressions. No hope of getting a complete set of rules for dealing with them. Halfway in the middle of this, we have exponential expressions, where we're allowed rational numbers, I, so we can do complex numbers, just the one variable x, addition, subtraction, and multiplication, and e to the x. So if we have an expression, we can actually take e to the power of that expression, and that's a new expression. In this case, there might be a canonical form depending on a big open conjecture, which is called Schanuel's conjecture, which essentially just says the thing that we want, which is that there's no surprising equivalences within this language of exponential expressions. There's no sort of complicated expression that we can make involving e to the x that's like equal to another complicated expression for non-trivial reasons. In other words, it's an open conjecture whether all of the exponential rules that we're used to suffice for working with exponential expressions. So thanks for watching. I realize this is a bit of an esoteric topic, but it's something that's really important to me, both as an algebra teacher and as somebody who's really interested in formal reasoning. First of all, it's really important that when we teach our students algebra, we make sure that they have, at the very least, a complete set of rules for dealing with whatever domain of algebra we're working in. And ideally, we'd like more than that. We'd like rules that also make it convenient to work within that domain of algebra. And I do hope one day to create this computation assistant program for making the process of working through an algebra problem step by step in a very formal way, very easy and very tactile, so that students can get a sense of what an absolutely formal algebraic calculation looks like. It helps them understand, like, what's the big picture? How is everything connected? What does it actually mean to show your work within algebra? And it would allow students to practice these high-level decision-making procedures even before they have all of the low-level actually applying the rules down to a point where they can reliably apply the rules without making mistakes. I'll be sure to keep you informed about the process of this project as it goes along, but for now, if you have any questions or comments, feel free to leave them down below, and I hope to see you in the next video.